Alright, so today we're going to do lesson 1.1. This is mostly a review. You've probably seen this before in some capacity, whether it's in your Algebra 1 class, your geometry class, or maybe even chemistry if you've taken chemistry or you're in chemistry right now. It starts on page 7 in your volume 1 books. You will also need the reference page A77, so go ahead, turn to page A as in apple 77 in the back of your books, tear that out, and have that ready to use. Pause the video for as long as you need to get that page out, but then go to page 7. Alright, so starting at the first set of notes in 1.1. Using ratios and proportions. We've seen ratios and proportions before. A ratio is just a comparison of two quantities. And a proportion is an equation showing that two ratios are equivalent. So if we have the two ratios A to B and C to D and they're equivalent, then we can write it as in a proportion. A over B equals C over D. Alright, example 1, using ratios. So this ratio problem or proportion problem is going to be something that you saw in geometry. If you remember the topic, similar triangles. So looking at my picture, I've got two right triangles, so they're similar. And they're asking, can the tree fall onto the house? So I need to know the height of the tree to see if it'll fall on the house. So I'm going to set up my proportion, and your book might have a different solution. Just remember, if you set up a proportion, you have to keep the two different values straight. So if I make a proportion using the small triangle first with the person, so 6 over 8, then my triangle for the tree needs to match. So since I use 6 on top, I need to use the height of the tree on the top here and the length of the shadow on the bottom. So my proportion is 6 over 8 equals h over 30. You guys used the butterfly method most likely when you learned this. So you took 6 times 30 and you set that equal to 8 times h. And then you just solve that. So 6 times 30 is 180 equals 8 times h. And then we divide both sides by 8. Which would give us, I believe, 22.5. But let me check. 180 divided by 8. Yes, 22.5. So the height of the tree is 22.5 feet, which means that if it were to fall, it would not fall on the house. Because it doesn't quite reach that distance. So since it is shorter, I'll start writing on the side, then 25 feet. Alright, so self-assessment problems. The first 4, do these on your own, pause the video, and then replay it to check your answers. Don't take more than about a minute per proportion. Okay, so answers. X over 3 equals 12 over 18. Butterfly method. X times 18 equals 12 times 3. 18x equals 36. Divide by 18. So x equals 2. Second one, 16 over y equals 8 over 5. Butterfly method. 16 times 5 equals 8 times y. 16 times 5 is 80. Equals 8y. Divide both sides by 8. So we get y equals 10. Alright, I'm going to clear this screen, so pause it if you're still writing. Number 3, 10 over 4 equals 6 over z. So we got 10 times z equals 6 times 4. 10z, I'll make that more obviously a z, equals 24. Divide both sides by 10. Z equals 2.4. And then last but not least, 9 over 16 equals n over 12. We got 9 times 12 equals 16 times n. So 108 equals 16n. Divide both sides by 16. Did not mean to do that. And we get that 6.75 equals n, or n equals 6.75. All right, moving forward. The next self-assessment problem I actually want to talk about with you guys. So we have the equations a over b equals c over d and AD equals BC. And they're asking, are they equivalent? And so what you guys know is that we can butterfly method, right? And we get a times d equals b times c. And so that does match this. The only thing I want you guys to think about is we have fractions, right? And what is the one instance where a fraction does not work? And it's when we have 0 in the denominator. This would be undefined, right? But in my second equation, if I made d or b 0, that would just be 0 equals 0, right? Which is not undefined. That works. So the answer to this, so as long as b and d do not equal 0, they are equivalent. So you always got to be careful with the fraction problems. And remember that you can't have 0 in the denominator. All right, last self-assessment problem. So go ahead and pause, work on this problem, and then come back and check your answer. All right, so you are 6 feet tall. So that's you. Your shadow is 4 feet 3 inches. Okay, there's also a water tower. We don't know its height, but we know that it casts a shadow that's 72 feet 3 inches. The first thing I want to do is get this where it's out of feet and inches. I want it to be one measurement. So I'm going to convert inches to feet, since they're both 3 inches, by dividing by 12. So that means I have 4.25 here and 72.25 here. All right, so I'm going to set up my proportion just like I did in my first example to find the height of the water tower. So my person's proportion, 6 over 4.25, equals my water tower's ratio, h over 72.25. And then I'm just solving for h. So 6 times 72.25 equals 4.25 h. 6 times 72.25 is 433.5. And then we divide both sides by 4.25, sorry. And we find that h equals 102. So the water tower is 102 feet. All right, pause if you're still writing, and then I will work on the second part. Okay, each additional foot in tower height increases the water pressure at the base of the tower by 0.43 pounds per square inch. So I got this water tower, right? And it's 102 feet. Each foot increases the water pressure by 0.43 pounds per square inch, or PSI. If I want to find the water pressure of the whole tower, I'm taking 102 feet times 0.43 PSI per foot. So 102 times 0.43 is 43.86 PSI. That is the water pressure at the base. All right. Next main idea in this section is rates. So a rate is a ratio of two quantities using different units. So if I have meters per second, then I can write it as 10 meters over seconds, or 10 meters per second, 10 meters per second. You guys are probably going to see this the most in your real life as miles per hour. That's probably the most common rate you will see. But all right, we can use rates to compare performances. So looking at this diagram, we have stats for a baseball pitcher. I can choose any rate that I want to compare. So if you're a baseball fan, you might choose a different rate. It depends on what you want to compare. So if I'm looking personally, I think I would want to know, like, maybe how many runs per strikeouts he got, maybe. So that's the rate I'm going to use. And you'll notice in your book that they use two different examples to show you that you can use any rate. So in 2019, his earned runs was 19, and his strikeouts was 100. So if I have 19 over 100, that's 0.19 earned runs per strikeouts. Okay, in 2020, he had 15 earned runs and 73 strikeouts. So I'm going to divide 15 by 73. That's one I can't do in my head. And I get about 0.21. I'm going to round to the nearest hundredth. So the pitcher, if I want to summarize this, I'm going to say the pitcher had, don't know why I did that, had more earned runs per strikeout in 2020. All right, so for self-assessment, I want you guys to do this on your own. You're going to get a bunch of different answers for this, so I'm not going to give you one set answer. Just find one that you like, and maybe compare it with the neighbor if you have time. So pause and work on this, and then come back. All right, so we're skipping that second self-assessment problem. We're going to the next main topic, using unit analysis. If you are currently in chemistry or you have taken chemistry before, this is something you will see in that class. And so when I'm working with units, if I want to convert units, I'm going to use what's called unit analysis. The way your book does it is a little different than what you'll see in chemistry. I'm going to show you what you'll see in chemistry just so you can keep that straight in your head. So this is where you'll need page 877 out of the back of your book. So example 3, we're converting 4.8 gallons to fluid ounces. The way we're going to do this, I'm going to set up this little like table almost. And what I start with goes right here in my top left corner. And I want to end with fluid ounces. So looking at my conversions, there's nothing that's gallons to fluid ounces, but I know I can go from gallons to quarts, quarts to pints, pints to cups, and then cups to fluid ounces. So that's what I'm going to do. So gallons to quarts, I have 1 gallon per 4 quarts. And I want to make sure I put these across from each other so that they cancel out. Okay, and then I go from quarts to pints. So 1 quart is equal to 2 pints. Pints to cups, 1 pint is 2 cups. And then cups to fluid ounces. So 1 cup is 8 fluid ounces. So what's happening here is each thing is canceling. I have gallons canceling, quarts, pints, and cups, and I'm left with fluid ounces. And then I'm multiplying everything in my top, everything in my denominator, and then dividing the two. So in the top, I have 4.8 times 4 times 2 times 2 times 8. In the denominator, I have a bunch of 1s. I know if I multiply 1 times itself, it's just 1. And so in my calculator, I'm going to do this math. 4.8 times 4 times 2 times 2 times 8 is 614.4. And my unit is what I ended with, fluid ounces. All right, my next example, we're talking about wind speeds on Jupiter and Neptune. So Jupiter is 180 meters per second. Neptune is 1,200 miles per hour. So now I'm converting a rate, and I can choose either one. I can either make my meters per second turn into miles per hour or miles per hour turn into meters per second. It doesn't matter. But I'm just going to work with Jupiter's and change it to miles per hour. So with a rate, what you're going to do, 180 meters per second. So second goes on the bottom here. The first thing I want to do, it really doesn't matter which one you choose. You can go from seconds to hours first or meters to miles. But because seconds to hours is something I know, I'm going to start with that. Because seconds is in the bottom, I'm putting it in the top here. I'm going to go seconds to minutes. So there's 60 seconds in 1 minute. And then minutes to hours, 60 minutes, 1 hour. Okay, so that cancels out seconds and minutes and gives me hours. And then I want to go meters to miles. So looking down here, I can go meters to feet and then feet to miles. Or I could go meters to kilometers and then kilometers to miles. It's all up to like what you are more comfortable with. But I'll do feet. So 1 meter is 3.28 feet. And then I'm going to come down here because I'm running out of space. Okay, and then I'm going to go feet to mile. So there's 5,280 feet in 1 mile. All right, so that's canceling out meters and feet and giving me miles. So what I'm doing is I'm multiplying everything in my top. So 180 times 60 times 60 times 3.28 times 1. And then everything on bottom, 1 times 1 times 1 is just 1, times 5,280. So that, in my calculator, 180 times 60 times 60 times 3.28 times 1. That equals 2,125,440 over 1 times 5,280. So divide that, and you get about 402.55 miles per hour. And so when I'm comparing Jupiter to Neptune, Jupiter is 402.55 miles per hour. Neptune has wind speeds that reach 1,200 miles per hour. So Neptune has the faster wind speeds. So my answer to that question would be Neptune has faster wind speeds. All right. So we got some self-assessment problems. Pause the video, work on these self-assessment problems, and then come back for your answer. So 3.2 meters, we want to get to inches. I'm going to go from, I can go straight from meters to inches. So 1 meter is 39.37 inches. So that equals 3.2 times 39.37 over 1. 2 times 39.37. Round to the nearest hundredth, that will be 125.98 inches. All right, pause if you're still working. Next self-assessment problem, go ahead and pause, and then come back and check your answers. 67 gallons per minute. Going from liters, or going 2 liters per second, so minutes to seconds of 1 minute per 60 seconds. And then gallons to liters. I have a conversion from that to that, so 1 gallon is 3.79 liters. So 67 times 3.79 over 60. 67 times 3.79 is 253.93. Divide that by 60. We get about 4.23 liters per second. Excuse me. Okay, and our last self-assessment problem. Again, pause, work on it, and then check your answer. Okay, a solar-powered plane travels around Earth. Its cruising speed is 90 kilometers per hour during the day and 1,000 meters per night, or per minute at night. So we're comparing. I'm just going to switch the day over to the night. So 90 kilometers per hour. And if you did the opposite, that's fine too. Just make sure your answer matches. So 90 kilometers per hour, I'm trying to go to meters per minute. So hour to minute. 1 hour has 60 minutes. Done. Kilometers to meter. I know that 1 kilometer is 1,000 meters. Okay, so I'm done there too. So 90 times 1,000 over 60. It's going to be 90,000 over 60, which I'm going to do in my calculator. 1,500, and that's in meters per minute. And so the daytime is faster than the nighttime. That means that he slows down at sunrise. All right, so that's it for 1.1. Make sure you are working on your homework. It's on the board. It's also in Google Classroom. And that will be due, I think, for your class September 12th. That's also on the board.